Welcome to this episode of Robert's Creative Chronicles. So today we'll be solving this question, which states that given that z1 is equal to 3 plus 5i, z2 is equal to negative 5 plus 4i, z3 is equal to negative 2 negative 3i, and z4 is equal to 7 minus 5i. z4 is equal to 7 minus 5i. A. Represent the complex numbers on the argand diagram. B. Find the modulus on the argument of z1, z2, z3, and z4. So solution. So we'll start with the A part. So let's represent these complex numbers on the argand diagram. So the argand diagram is nothing but the Cartesian plane. So we'll draw, since there are many, let's represent them at once. So now here, this is the x-axis, this is the y-axis, then this is the origin. So now z1 is 3 plus 5i. So z1 is 3 plus 5i. So that means, and you know, a complex number has a real component and it has an imaginary component. And the real component is denoted by x, and the imaginary component is denoted by y. So x here is 3 and y is 5. So on the x-axis, here's the positive x-axis, we will find 3 here. So, but since we are going to locate all these numbers, on this Cartesian plane, we are going to mark the scale on it. So since the highest number here is 7, on each one we'll mark 1 to 7. Likewise here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So here is 1, 2, 3. Here is 3, 4, 5, 6, 7. 1, 3, 5, 7. So here is negative, 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 negative. Here is also negative, negative 3, negative 5, 6, negative 7. You can label all of them if you want, or let's just label all of them. So this is negative 2, negative 3, negative 4, negative 5, negative 6, negative 2, negative 4, negative 6, 2, 4, 5, 6. Yes. And there you have it. So now the first one is 3 plus 5i. So here is 3. Here we'll find 3 here, which is here. Then 5. So it will be like this. Then 3 like this. So it will be at this point. So this is z1, which is equals to what? 3 plus 5i. Then we'll join it to the origin. Yes, so this is z1. So here is z1. The x component is 3 and the y component is 5. So the next one, z2. The x component is negative 5. That is here, negative 5. And the y component is 4. So it will be negative 5 here and 4 here. So it's here at this point, negative 5 and 4. So here will be z2, which is equal to what? So z2 is negative 5 and 4, which is here. X component is negative 5, y component is 4. So here is negative 5 plus 4i. So here also is negative 2 and negative 3. So this one is x component is what? Negative 2. And y component is negative 3. So here is what? Z3 is negative 2, negative 3i, negative 3i. So you join it. This is Z3. This is Z3. Then Z4. And we have not even joined Z2. So Z2 also you join it. Then the last one Z4. And then the last one Z4. Z4, the x component is 7 here. And the y component is negative 5. Here. So here is Z4 is equal to 7 minus 5i. So then you join it. So this is Z4. So this is the argand diagram, and which is showing all the 4 complex numbers. This part, you can use a pencil to trace it out. This part, to make it, or you can just use your hand. You don't need to, or anyhow you want to do it, you can do it anyhow. No, I'm just trying to show you the numbers, the one on the axis, so you know you not think I'm taking the, so you know the axis I'm taking each number for. So now let's move to the B part. Find the modulus and the argument of Z1, Z2. Find the modulus and the argument of Z1, Z2, and Z1, Z2, Z3, and Z4. So now let's move to B. Now the modulus. The modulus is also known as the absolute value. So it has its own formula. It's given by, this is the modulus of Z. This is equals the modulus of x plus iy, which is, this is the complex number, which is equals to the square root of x squared plus y squared. Now the argument of a complex number. The argument of a complex number is the positive angle between the complex number and the positive real axis. This is the positive real axis. This horizontal x-axis from this point here. It doesn't include here, only from this point 0. Here, this is the positive real axis. So it's the positive angle. So argument cannot be negative. It must be a positive angle from the measured in anti-clockwise direction from this axis. This one, this positive real axis or positive horizontal axis. From here going, and it is measured in anti-clockwise direction. So now, from here to here will be an argument. 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 So let's do it. Z1. And the argument is given by, the argument of a complex number is given by theta, which is equals to tan inverse y over x. So let's do this. So Z1 is 3 plus 5i. Z1 is 3 plus 5i. Now let's find this modulus. Modulus of Z1 is what? 3 square plus 5 square. Because this one is x, this one is y. So this is what? Is 34 root of 34. So this one is root of 34. So this is the modulus of z1. And then the argument of z1 is what? Is tan inverse. Which one is y? Is 5. Which one is x? 3. So what's tan inverse 5 over 3? 5 over 3. 59.04. So this is 59.04 approximately. This is 59.04 degrees. So that's the argument of z1. And that means from the definition of argument, this is the angle and it's measured in anticlockwise direction. And this is 59.04 degrees. So now the second one, z2. z2 is what? Minus 5 plus 4i. Is minus 5 plus 4i. Then the modulus is equals to what? Minus 5 square plus 4 square. Minus square is plus, so there's no need to put the minus in the calculator. So it's root of 41. That's the modulus of z2. And this modulus, to show, you can show the modulus on the diagram. The modulus is the length of this line. So that means this line, now this line z2 is root of 41. This line z1 is root of 34. It's given by, it's also another symbol that is used to represent modulus of z1 is r1. This one is r, the modulus of z is r, modulus of z1 is r1, and this is r2. That is the distance from here. Because normally if you even use Pythagoras theory, it will be 3 square. This square will be equal to this square plus this square. So if you to find this one, you find the square root of the sum of the square of these two to find this. That is the square root of the sum of the square of this. That is it. This is the square root of the sum of the square of the two. And likewise this. So this plus this square plus this square, then you find the square root. You get this. So this even follows Pythagoras theory. So now the argument of z2 is equal to tan inverse y is 4 over minus 5. So it will be tan inverse 4 over minus 5. This is minus 38.65. Now this is negative, and this is in the second quadrant. This is in the second quadrant, and it's giving us a negative angle. So what we will do is we'll add 180 to get the distance, the positive angle from this positive axis to this line, which is the definition of argument. So we have to add 180 because it's in this quadrant. Because argument cannot be a negative angle. So since it is in the second quadrant, we will add 180 to it. So this is what? Negative 38.66 approximately. Then we'll add 180 to it. We will say this since it's the second quadrant plus 180 degrees. So this will be minus 38.66 plus 180 degrees. which is 141.34. So it's 141.34 degrees. So this is the argument. This is the argument, this is the answer. So the argument that is from here. So that means the distance from this positive real axis to this line is 141.34 degrees. So we'll put it from here to here is what? So from this positive real axis to here is what? 141.34 degrees. So then the third one, Z3. Z3 is what? From above here, Z3 is minus 2 minus 3i. So the modulus of Z3 will be negative 2 square plus negative 3 square. So this will be what? 2 square plus 3 square, negative 13. This is the modulus of Z3. That means the distance from this point to Z3 here is root of 13. So now the argument of Z3 is what? Tan inverse y is negative 3 over negative 2. That is 3 over 2. Tan inverse 3 over 2. Tan inverse 3 over 2. Now, the first one we got was positive. We didn't need to manipulate it. But the actual reason we didn't need to manipulate that one, it wasn't because it was only positive. It's because it is positive and it's also in the first quadrant. So since it's positive and the first quadrant, from this diagram, you know that yes, it is actually 59 because because 59 is less than 90 degrees, and the point is here, and the point is here. Here you can see that it's obviously 141 because it will be less than 180. So here must be greater than 180 but less than 270. From here, it must be greater than 180 and less than 270. That is because it's in the third quadrant. So we have to add 180 to it. This is the angle that was found from the calculation. That is 50. Here is 56.31. So we will add 180 to it to find the actual angle from the positive real axis. So we have to add 180 to it because it's in the third quadrant. So here, this is 56.31. 56.31 plus 180. So 56.31 plus 180 is 236.31. So this is 236.31 degrees. You can see that it's obviously 236.31 because this will be greater, the angle to here will be greater than 180. Will be greater than 180, but will be less than 270. So now here, this angle also should be greater than 270 or less than 360 because in the fourth quadrant. So let's find it. So now Z4 is what? Is 7 minus 5i. Now the modulus 7 square plus minus 5 square. Okay, it's positive. So it's root of 74. So here will be root of 74. Then the argument of Z4 will be equals to tan inverse minus 5 over 7. So now, then we'll do tan negative 5 over 7. Tan negative 5 over 7 is minus 35.54. Minus 35.54. Approximate. So now from the diagram, you can see that Z4 is in the fourth quadrant. So now that means it will be greater than 270, but less than 360. So therefore, we'll add 360 to it. Since it's negative, it will reduce. So it will be between 270 and 360. So this plus 360. So negative 35.54 plus 360 is 324.46. So this will be 324.46 degrees. So this is the argument of Z4. So you can see it. So now you can see that the distance, okay. As for Z3 is what? Is 236.31. 236.31. So we'll write it here. So the distance from here to this one is what? 236.31. Then here will be what? The last one. The last one is what? The last one is what? 324.46. So this one is 324.46. So that's it. These are all the arguments of this complex number with the complex number itself. Then this one, you can see that the distance of this one is more than all the other distance. That means the modulus must also be more than them. So Z4, the modulus of Z4 is what? Is root of 74. You can see that actually is more than root of 13, root of 41, and root of 34. So actually is correct. So that means we will find all the modulus and all the arguments of this complex number. I hope you understood this episode. If you have any question, feel free to contact me using my WhatsApp or email written in the description below, or you can write them in the comment section. Thank you for watching. Please don't forget to like, share, and subscribe to my channel, and hit the notification bell to get notified as soon as I drop a new video. Thanks.